Imagine you are trying to upgrade your home entertainment system, right? And you decide to go with a highly modular approach.
Oh, man. That is usually where the trouble starts.
Yeah, exactly. So you start with this massive display, but then, you realize you need a separate receiver just for the audio decoding.
Right, because the built-in speakers are terrible.
Exactly. Then you buy a dedicated cable box, then a specialized streaming device just for 4K content, then a separate digital to analog converter for your high-fidelity music.
And before you know it, you're out of counter space.
Totally. Suddenly, your living room looks like a server room. You have this massive tangle of HDMI and optical wires, overlapping frequencies, heat generation issues, and like 5 different remotes just sitting on your coffee table.
Yeah, it becomes a textbook example of operational overload. I mean, you are trying to achieve a single outcome just watching a movie, but the infrastructure required to route all that audio and video has basically become a part-time job to manage.
Yeah, it's exhausting.
When hardware scales laterally without integration, you inevitably hit a wall of diminishing returns.
And that architectural nightmare is fundamentally what happened to enterprise network security in the early 2000s. I mean, the tangle of wires just got so out of hand that the industry was forced to invent a completely new paradigm for traffic management.
Absolutely.
So welcome. You are listening to the WeCyberYou Unlocked podcast, WeCyberYou. But today, we are skipping the usual format. This is a deep dive into our source material. Specifically, we're looking at a massive architectural document called Unified Threat Management, the Comprehensive UTM Firewall Guide.
And this guide doesn't just, skim the surface. It really breaks down the mechanical evolution of modern network defense. It dissects how we moved from those isolated choke points to, highly orchestrated inspection engines.
Right. So our mission today is to act as your shortcut to being completely well-informed on this architecture. We are going to take you from the absolute chaos of 1990s network security all the way to today's all-in-one AI-driven protection platforms.
Yeah, we want you to understand not just what a UTM firewall is, but the underlying mechanisms, like how it actually processes traffic under the hood.
Okay, let's unpack this. To really grasp the engineering behind unified threat management, we first have to look at the operational mess that forced it into existence.
Yeah, the first generation of enterprise security back in the 1990s was structurally very rigid.
Very basic stuff, right?
Extremely basic. Organizations relied almost entirely on simple packet filtering, firewalls, and routers. And they used standard access control lists, or ACLs.
Just simple block or allow rules.
Exactly. They were largely stateless, meaning they just evaluated the source IP, destination IP, and the port number.
Right.
If the traffic matched the rule, it passed. If it didn't, it dropped. There was no real context, or memory of the connection state.
So as threats evolved beyond basic port scanning, simply checking the outside envelope of the data just wasn't enough anymore. And that's when we entered the second generation.
The era of massive appliance sprawl.
Right. As application layer attacks became more sophisticated, organizations reacted by, basically buying dedicated physical devices for every newly discovered vulnerability.
Which created the daisy chain of death for network latency.
The daisy chain of death. I love that term. How did that actually look in a server room?
Well, a data packet would arrive at the perimeter firewall. From there, it would physically route over a cable to a dedicated intrusion detection system, then to a separate web filtering proxy, then maybe to a standalone spam filter or, an email gateway. Every single hop required the data to be processed, analyzed, and retransmitted by a completely different hardware box.
So it's the ultimate kitchen analogy again. Imagine trying to cook a complex meal in a kitchen where you have a separate appliance for like a toaster, a blender, a coffee maker, and a waffle iron.
Right, taking up all the counter space.
Exactly. Each one requires its own power source. And most importantly, each one has a different instruction manual, which, in the networking world translates to separate licensing agreements, distinct management consoles, and proprietary operating systems.
Yeah, it creates a massive maintenance headache, and that sprawling approach drastically increased the attack surface just through sheer complexity.
How so? Just because of the number of boxes?
Partially, yeah. Think about the operational costs of powering, cooling, and racking 10 different physical boxes. But the real danger was administrative friction.
Oh, like human error?
Exactly. When an IT team has to log into 10 disjointed management interfaces to update rules for a single zero-day vulnerability, configuration errors are mathematically guaranteed.
Because they miss one box.
Right. A policy gets successfully pushed to the web proxy, but it completely fails to deploy on the intrusion prevention system.
And so you end up with a porous perimeter simply because the tools cannot communicate with each other. So the industry recognized this breaking point, which leads us to the third generation. The UTM, Unified Threat Management, was basically the mandate to consolidate all those sprawling kitchen appliances into one master chassis.
Right. A centralized interface, a unified policy engine, and a single operating system managing all major network security functions.
By collapsing the hardware, you eliminate that physical routing latency between the distinct devices. But the internal challenge becomes staggering. Like, how do you take a network firewall, layer in real-time antivirus scanning for ransomware, and stack application control on top of it without bringing the CPU to a grinding halt?
Well, let's contrast how the UTM integrates those features compared to the old standalone models. The source emphasizes the evolution from IDS to IPS, so intrusion detection versus intrusion prevention.
Right, because the standalone systems of the past often sat passively out of band, right?
Yes, and IDS traditionally relied on port mirroring. It just received a copy of the network traffic, analyzed it for anomalies like port scanning or known exploit signatures, and generated a log or an alert.
It was just a passive observer. It couldn't actually stop the attack.
Exactly, but the transition to the UTM heavily favors the IPS, which operates in line. Because all traffic must flow physically through the UTM's interfaces, the IPS engine actively interrupts and drops malicious packets in transit.
So it's actually killing SQL injections and cross-site scripting before they ever reach the target server.
Exactly.
We also see a massive leap in application control here, because a traditional layer 4 firewall sees traffic on port 443 and just categorizes it as generic secure web traffic.
It doesn't know what it actually is.
Yeah, but the UTM is doing deep packet inspection to identify the actual application layer signature. It can distinguish between a user accessing Salesforce versus a user firing up a BitTorrent client.
Even if both are attempting to use the exact same standard web ports.
Right, so you can explicitly allow Zoom for business continuity while silently dropping unauthorized shadow IT applications.
What's fascinating here is how the architecture handles the reality of modern encryption. We just mentioned deep packet inspection, but over 90% of all internet traffic today is encrypted via HTTPS.
Oh, yeah.
A standard firewall looking at an encrypted payload sees nothing but randomized mathematical garbage.
Wait. So if the payload is wrapped in a secure encrypted tunnel from the user's browser all the way to the bank's server, how does the UTM's antivirus engine even see the hidden malware? I mean, doesn't the encryption completely blind the UTM's internal engines?
Well, it would, if not for SSL/TLS inspection. The UTM essentially acts as an authorized cryptographic middleman.
A middleman? How does that work?
When an endpoint inside the network attempts to establish a secure connection with an external server, the UTM intercepts that handshake.
Okay.
It establishes its own secure connection with the external server, retrieves the data, decrypts it internally, runs the unencrypted payload through the antivirus and IPS engines.
Wow, so it actually opens it up.
Yes. And then it re-encrypts the clean data using its own internal certificate before passing it to the user.
That is wild. It intercepts the armored transport, unloads the cargo, runs it through a chemical sniffer, repackages it in a new armored car, and sends it on its way. And it does all of that in milliseconds.
Yep.
I mean, that requires an unbelievable amount of processing power.
It is incredibly resource intensive.
Yeah.
I mean, early UTMs were notorious for choking when SSL inspection was turned on, because cryptographic math taxes standard CPUs really heavily.
So how do modern ones handle it?
Modern UTMs solve this by incorporating dedicated hardware ASICs, application-specific integrated circuits. These are designed exclusively to handle the encryption and decryption math, which offloads that burden from the main security processors.
Okay, so knowing the tools inside the box, the hardware acceleration, the IPS, the application signatures, it brings up the structural mechanics. Like, when a user clicks a link to download a file, how do all these separate security engines fire off simultaneously? Do they take turns scanning the packet?
Not exactly. The source outlines a highly structured 7-step gauntlet of traffic analysis. Every single packet of data has to survive this gauntlet. Step 1 is arrival. The packet physically hits the ingress interface.
Makes sense. And then step 2 is session validation.
Right. This is where the stateful inspection happens at the transport layer. The UPM evaluates the TCP sequence numbers and flags.
So it's asking, is this part of an established three-way handshake? Does this packet belong to a legitimate, ongoing conversation? Or is it an unauthorized SYN packet trying to force a new session?
Exactly. And if it violates stateful logic, it gets dropped immediately at step 2.
Good riddance.
Right. But assuming it passes, we move to step 3, traffic classification. The UTM maps the packet's source IP to an authenticated user identity.
Okay.
It identifies the device posture, parses the server name indication to identify the destination domain, and classifies the specific application protocol.
Got it. And here's where it gets really interesting. Step 4 is deep inspection, and this is where the magic of modern architecture shines. I look at this like a highly advanced airport security checkpoint.
I like that analogy.
Right. Instead of making you walk through an ID check and then stand in a separate line for the metal detector, and then a separate line for the baggage x-ray, and then a separate line for a background check.
Yeah.
Well, everything happens simultaneously.
Yeah, you were describing single-pass architecture, which is basically the mechanical answer to the latency problem. Instead of queuing the packet through the antivirus engine and then moving it to the IPS engine and then moving it to the URL filter.
Which would take forever.
Right. Instead of that, the UTM maps a packet into a shared memory space once. All the different security engines like the malware scanner, the exploit detector, the AI heuristics, they all scan that exact same memory space in parallel.
Wow. They all look at the exact same data simultaneously, run their specialized checks, and report their findings, which triggers step 5, threat correlation.
If we connect this to the bigger picture, threat correlation is the engine that actually defines a modern UTM. It is a mathematical scoring system.
Okay.
Hackers know how to evade individual security checks, so the UTM looks for compounded suspicious behavior.
Can you walk us through a real-world scenario of how that scoring works? Like, what does that actually look like?
Sure. Imagine an employee receives an email and clicks a link. The domain is only 3 days old. The URL filter flags that as suspicious, assigning it a minor risk score, but not enough to block it outright.
Okay, slightly suspicious, but maybe it's just a new marketing site.
Exactly. Then the user downloads an executable file. The antivirus engine checks the file hash against known signatures, but it comes back clean because it's a newly compiled 0-day variant.
Uh-oh.
Right. However, the AI heuristics engine notices the file's code structure contains API calls commonly used for encrypting hard drives.
Like ransomware.
Yes. But legitimate software occasionally does this too, so it's not a definitive block yet. Finally, the IPS engine notices the destination server is hosted in a high-risk autonomous system block, one that's known for command and control infrastructure.
Ah, I see. So any one of those flags in isolation might just generate a low-level warning, but the correlation engine aggregates all of them: the newly registered domain, the suspicious API calls, and the high-risk server communication.
Spot on. It calculates a critical threat score, overriding the individual engines and classifying the traffic as malicious.
And that leads directly to step 6, decision-making. Based on that correlated threat score, the UTM enforces the policy. It can allow the connection, silently drop the packets, send a TCP reset to aggressively tear down the session, or route the payload into quarantine.
Right. And finally, step 7 is reporting, where the metadata of the entire interaction is logged to the centralized management console for the security operations team.
That parallel processing and correlation handles known threats and, slightly modified behaviors brilliantly. But you brought up 0-day variants earlier.
I did.
So how does a UTM handle advanced, never-before-seen attacks that have no existing signatures and actively attempt to bypass those heuristic checks?
The guide details the next-level defenses integrated into modern platforms, heavily leaning on cloud threat intelligence.
Cloud intel?
Yeah. The physical UPM appliance sitting in an office rack is essentially a localized enforcement node tied into a massive global neural network. Security vendors maintain vast cloud databases processing telemetry from millions of deployments worldwide.
So if a new botnet campaign launches in another hemisphere, the vendor's cloud analyzes it, generates an indicator of compromise, and pushes that update down to your local UTM within minutes.
Exactly. The local box doesn't have to discover the threat organically, it just inherits the global immunity.
That's incredible.
But for files that are entirely unknown, meaning they have zero global reputation, the UTM utilizes sandboxing.
Right, we've heard about this.
Instead of allowing a highly suspicious unknown executable onto the internal network, the UTM intercepts it and forwards a copy to an isolated virtual environment. This can be either locally on specialized hardware or up in the vendor's cloud sandbox.
So it essentially detonates the file in a heavily instrumented clean room. It executes the code and just watches what happens to the virtual registry, the file system, and the network adapters.
Right. If the file attempts a privilege escalation or tries to deploy a rootkit, the sandbox flags the hash as malicious.
But you have to consider the architectural friction here, right?
What do you mean?
Well, if you are pausing every single download to detonate it in a virtual room and wait for behavioral analysis, isn't the network going to grind to a halt? Like if I need to download a crucial PDF for a meeting right now, I cannot stare at a loading screen for 5 minutes while a cloud sandbox spins up a virtual machine.
That is the eternal tension between zero trust validation and user experience. But UTMs handle this through a few different methods. One method is TCP session holding, where the firewall tricks the browser into keeping the connection open with keep alive packets while the quick detonation occurs.
Oh, that's clever.
Yeah. But for larger files, many organizations configure the UTM to allow the download to proceed, but perform the sandboxing asynchronously.
Wait, so it lets it through first?
Yes, and if the sandbox subsequently discovers the file is malicious, say 5 minutes later, the UPM immediately alerts the endpoint detection software on the user's laptop via an API integration.
Oh, I see.
It instantly isolates the machine and quarantines the file.
So it is a calculated risk acceptance to maintain business velocity.
Exactly.
Speaking of zero trust, the guide mentions zero trust architecture, or ZTA, as a major component of these platforms. ZTA is the philosophy that you never implicitly trust any user or device, even if they are physically plugged into the corporate LAN. Does deploying a UTM automatically grant an organization a zero trust environment?
No, it provides the enforcement mechanism, but not the entirety of the architecture. Zero trust requires robust identity management, multi-factor authentication, and continuous device posture checking.
So where does the UTM fit in?
A UTM acts as the policy enforcement point. It facilitates microsegmentation, ensuring that, for example, a compromised smart TV in the conference room cannot communicate laterally with the accounting department's servers.
Got it.
The UTM enforces the least privilege access rules, meaning a user is only granted network pathways to the specific applications their role requires, blocking everything else by default.
Okay, so we have spent a lot of time discussing the capabilities of this unified architecture. It consolidates hardware, performs parallel deep packet inspection, decrypts SSL traffic via ASICs, correlates heuristic scoring, and enforces microsegmentation.
It does a lot.
It sounds like an impenetrable silver bullet. What is the catch? I mean, is there a systemic risk to putting all of your network security functionality into a single chassis?
This raises an important question about fault tolerance and infrastructure design. And the guide is very objective about the limitations.
Okay.
The most glaring architectural risk is the single point of failure. If an organization routes every packet, every VPN tunnel, and every email through one physical UTM appliance, and the motherboard fries, or a firmware update bricks the device.
Oh, man.
Yeah. All network transit ceases and all security services drop simultaneously.
You don't just lose your antivirus. You lose your routing, your web filter, your external connectivity, everything. The network goes dark.
Yeah. Organizations mitigate this by deploying UTMs in high availability, or HA clusters. You basically deploy two identical hardware boxes.
Ah, redundancy.
Exactly. In an active path of setup, the secondary box sits quietly, constantly syncing stateful session tables with the primary.
So if the primary fails?
If the primary hardware fails, the passive box seamlessly takes over the IP addresses and routing tables within milliseconds, without dropping active user sessions.
Okay, that makes sense. The other limitation the source mentions is the throughput ceiling, because running multiple security engines simultaneously, especially SSL decryption, requires massive compute resources.
Huge amounts.
So if a company suddenly doubles its workforce and bandwidth, that hardware appliance might just max out its CPU, introducing severe latency as packets queue up waiting for inspection.
Which brings us to the distinction between a UTM and a next-generation firewall, or NGFW.
I always wondered about the difference between those two.
Historically, UTMs were designed for small and medium-sized businesses, branch offices, and retail chains. The goal was broad integration, giving an IT team of 2 people a single dashboard to manage everything from content filtering to basic routing.
Okay, and the NGFW?
The NGFW, on the other hand, was built for massive enterprise data centers.
Makes sense.
It's exactly. Enterprises with multi-gigabit throughput requirements just couldn't afford the latency of an all-in-one box. They wanted deep, specialized application awareness and hyperfast IPS throughput, but they preferred to keep email filtering or proxy services on separate, dedicated infrastructure to distribute the compute load.
But the guide notes that due to advancements in custom silicon and cloud computing, the technical distinction between a UTM and an NGFW has largely evaporated, hasn't it?
It really has.
The hardware has become so powerful that a single unified box can now handle enterprise-grade throughput without buckling. So, what does this all mean? When we evaluate the journey from those rudimentary packet filters of the 90s to the appliance sprawl of the 2000s, the UTM represents the maturation of network engineering.
I agree completely.
By converging the hardware and utilizing single-pass software architecture, organizations can achieve layered, correlated threat detection without suffering the operational paralysis of managing disjointed systems.
Yeah, you gain comprehensive visibility and control, restoring sanity to the infrastructure while actually elevating the security posture through unified threat intelligence.
Before we close out, we want to ask you to follow the channel so you never miss our analysis of the latest architectures. And make sure you visit WeCyberYou.com, for a massive library of content just like this deep dive.
And I want to leave you with a structural thought based on the future of UTM section.
Oh, let's hear it.
We've established that the UTM was masterfully engineered to protect the perimeter of a network, the physical gateway of an office building. But the modern workforce is entirely distributed now.
True, everyone's remote.
Applications live in cloud data centers, and users are accessing them from coffee shops and home networks. The traditional corporate perimeter has dissolved. So, if the perimeter no longer exists in a physical location, how long will the physical UTM hardware appliance survive?
That's a really good question.
Are we moving toward a secure access service edge SASE, where the entire UTM inspection gauntlet simply vanishes from the server rack and operates entirely as a decentralized cloud service?
Wow. We started by comparing this to a home entertainment system and the quest for one unified box. But the ultimate evolution might not be a better physical box at all. The future of the architecture might be the complete virtualization of the hardware itself. Definitely something to seriously consider as you map out your next deployment.